Let's have a look at our equations for work and energy. And here is our sheet. Now, I've gone through all of these in prior videos, but let's have another look at them. This one here is strictly force equals ma, Newton's second law of motion. This one here is the one that I prefer to use. The sum of the forces in the x direction is equal to mass times the acceleration in the x direction. And you will notice that in these equations, I also put in capital F with a subscript. This will be static friction, but I also put in capital F because friction is a force. The subscript S for static friction. Here is one for kinetic friction, capital F, which I wrote in. And I also use for weight. I put in a capital F, the sub W representing the force of weight, because weight is a force. And of course, we have the force of gravity. So all these can be represented with a capital F. And all forces have a unit of Newton. All forces unit of Newton in honor of Isaac Newton, and it represented by the capital N. Going down here to work and energy. First one that comes up is this one, and this is the equation for work. Work is equal to force times distance. And you'll notice that force is also a capital F. And hence the reason I put the capital F's up here, because these forces are what can be substituted into here. Or looking at it the other way around, this capital F represents one of these forces, whichever one it is that we happen to be working with at the time. They can be substituted. These ones here with the capital F's, all these are forces, are substituted here. Not the left-hand side where it says capital F. What we're interested in is the right-hand side. This is the working side. So if we were to take, say, this one here for weight, and if we wanted to substitute weight in here, we wouldn't just substitute the force of weight, because that's what this represents already. We would substitute it with mg. So the work done by weight, or someone pulling on a weight, will be represented by mg. Put mg in here. Look like this. Times the distance. And if we wanted to know how much work, say, kinetic friction is doing, well, this F then also represents kinetic friction. Now, of course, we're not going to put in F sub k here because we're no further ahead. We'll put in the right-hand side. So then the work done by kinetic friction would look like this. Work done, work, W stands for work. And we're going to substitute the right-hand side, normal force, times the distance traveled. And if we wanted to know in Newton's second law of motion how much work is being done by the sum of forces of pushing or pulling on an object, well, then this is also here. That F represents all of these F's up above. And we can just simply replace it with that, with the right-hand side. So work is equal to the sum of the forces in the x direction times the distance traveled. The net force times the distance traveled. And we can calculate the net force separately, or we can also use the right-hand side. Work done is equal to mass times the acceleration in the x direction times the distance traveled. So this F right here for work is basically a placeholder representing these forces up above. And let's look at it specifically now. Work is equal to a force times the distance traveled. S represents the distance. Distance. Putting in the units, work is equal, all forces have a unit of a Newton. All distances, regardless of whether it's a distance from here to here, or it's a distance from there to there, or some distance from some distance like this. All distances have a unit of a meter. So the right-hand side is a Newton meter. And Newton meters has a special name called a joule. So all work has the units of joules. Work is a form of energy. So then I can expand this and say all energy has the unit of a joule. And if I go to our base units, here it is here. These are our base units. And often I have said use the base units. And the reason I say use these base units because these then become the derived units. Looking down on here. And here is the Newton. And the Newton is a combination of kilogram meters per second squared. And if we look over here at the joule, well, the joule is a Newton meter. But a Newton is a kilogram meter per second squared. So everything here, kilogram meters and seconds, is a combination of the base units. Hence the reason I said you need to have our base units in order to put in our equations for the answer to be something reasonable. So that we all understand what it is because we are using the same units. And later on, we're going to see that a Newton per meter squared is also known as a Pascal. In order for these to make sense to us, we have to use these base units in our equations. Going on, looking at this one. Well, this is work being done on an incline. Consider, here's an incline at some angle. Oh, take that back. It's an object being pulled horizontally at some angle. There we go, that's better. That's the force. And we're interested in moving this horizontally along the x-axis. In order to do that calculation, we need to find the x component. And the x component, you already know. The x component is m cosine theta, because the theta is adjacent to the x component. And m represents the magnitude of the force that's being applied. So we can replace this with F. This being the force that's being applied. So F cos theta, that is the force along the x direction. And then work is equal to the force in the x direction times the distance traveled. And that's what our equation states. This is actually a general equation. Consider these two. Here is a horizontal plane, a floor. I have an item, and it's going to be horizontally pushed by an individual. He's pushing it from here to here. It has to travel a distance in order for work to be done. If it doesn't travel any distances at all, then the distance s becomes 0, and the whole term is 0, so no work is done. We consider this scenario. I'm going to apply a force. For the sake of argument, let's say he's applying a force of 24 newtons, and he's going to travel from here to here, a total of, to make it easy numbers for me, 2 meters. Therefore, the work done is equal to the force times the distance. Using this equation here, everything is horizontal. Force applied is 24 newtons times 2, and that'll be 48. And the unit of work, we just said earlier, can be a Newton meter, also known as a joule. We use in this equation, work done is equal to the force cosine of the angle. The angle here, theta, is equal to 0. It's not on an incline. Everything is 0. Cosine of 0. Now that's not theta, that should be 0. Times the distance traveled. Cosine of 0 is 1. So we put in the numbers, 24 times the cosine of 0 is equal to 1. times the distance traveled. And that's putting down to 24 times 1 times the distance traveled is 2, or back to 48. So this equation can still be used for something that is completely horizontal. But if we're pulling it some force at some angle, then we'll need to use this equation. F, let's do this F right here, happens to be, we're going up here, 30 newtons at some angle here, say 10 degrees. And it's going to travel that distance. And the work done, well, we have to use the component of this along the horizontal. And that component is F cos theta. And the work done in this scenario, simply a matter of putting in the variables into this equation, which you already understand because that is the component, the x component. The applied force, 30 newtons. Cosine the adjacent angle, 10 degrees, times the distance it's going to move. We're going to move from here to here along the horizontal, 2 meters. And I won't be doing the math for this, but you get the general idea. And below that, we have kinetic energy. KE stands for kinetic energy, and I wrote it here. Kinetic energy is equal to, KE is equal to 1/2 times the mass of the object, times its velocity squared, to the power of 2. So we have an item. Here's a car. And it's going down the road. If it is parked, somewhere, its velocity is 0, therefore its kinetic energy will be 0. Kinetic energy for something that is parked is 1/2 times its mass, regardless of what the mass is. The mass isn't going to change. So let's call this 1,000 kilograms times its speed. It's parked, it has 0 speed, so that's 0. Its kinetic energy is 0. So kinetic energy is based on its speed. It has to be moving in order to have kinetic energy. And if it starts up and it starts to move forward at some speed, we'll use easy numbers, 2 meters per second. Its velocity is now 2 meters per second. Then its kinetic energy is going to be 1/2 times its mass of 1,000 kilograms times its speed of 2 meters per second, everything squared. That's what this represents. Everything squared, including the units. So if we work out the units on this one, kinetic energy is equal to 1/2 of 5,000 or 1,000. 1/2 of 1,000 is 500 kilograms times 2 operates on the 2 on the meters and on the seconds. That would be 4 meters squared per second squared. $500 times 4, I think that's 2,000. That'd be 20. 2,000, and the units left over is kilograms meters squared per second squared. Kinetic energy is energy, and I said earlier, all energy has the unit of a joule. Looking at this combination of units, let's split up the meters. Kilograms times meters divided by seconds squared. This combination of units we now know is a Newton times a meter, and a Newton times a meter is also a joule. And we have it here. A Newton meter is also a joule. So kinetic energy is a function of speed, and it has the units of joules. Now let's look at the next equation, potential energy. This is gravitational potential energy. And I talk about this in another video. And it has to do with height. Is equal to the mass of an object times g times the height. So here's an object, here's the ground, and we have an object. Here's a ball. And we're going to raise the ball upwards. It doesn't have a motor on it, nothing like that. It's just simply being raised upwards. And the individual who's doing the lifting, so he's going to lift it up to here, let's say. And the height that it is being raised to from the ground to that height, we'll call that height, again for easy numbers, 1 meter. Lifts it up 1 meter. That's what h represents. And h is a distance. 1 meter is a distance. And if we look at the object, its mass down here is exactly the same as the mass up here. It hasn't changed anything, hasn't dropped anything, hasn't fallen apart. It's still the same mass. G is a constant. G is 9.8 meters per second squared. It's not going to change over this little distance, so it's a constant. But what does change is h. So potential energy is a function of height. The higher something is, bigger the number here, the bigger that number, the bigger the potential energy. The lower this number, the lower the potential energy. And if this goes all the way to 0, at 0.0 right here, this is a reference, and we're going to call this the 0 reference. The height at this point here is 0, so when that is 0, potential energy is 0 at this point. So potential energy is a function of height. Whereas kinetic energy is a function of velocity. The faster something is, more kinetic energy it has. The higher something is, the more potential energy it has, and vice versa. The lower it is, the less potential energy. This one here, in the case of height, we have an object up here, and we're going to drop it. It's now going to drop. Two things happen as it drops. Its speed is going to increase. Because its speed is increasing, that means its kinetic energy must be increasing. But its height is also decreasing, this being the 0 point. Its height is also decreasing, so its potential energy is also decreasing. So as one goes up, the other goes down. At any point right here, it has a total energy. Its kinetic energy and add up its potential energy. That will be its total energy at this point. We can calculate the kinetic energy, we can calculate the potential energy at that particular height. Let's say we give this height here 1.5 meters, and the whole thing here was say 5 meters up. We can calculate what its speed is here, that in turn we calculate its kinetic energy and its potential energy. So its total energy at this level is a combination of these two, the addition of those two. That's really not too important for us. This represents total energy. But that total energy comes into play in the next equation, right here. And this is the conservation of mechanical energy. And what it simply means is all of the energy that you start with, that's right here, I got it on the right-hand side, must equal all of the energy that you finish with. And that's it's an extension of total energy. Total energy on the left-hand side must equal the total energy on the right-hand side. And I went through another video explaining this one here in detail. And the subscripts, 1/2 mass velocity, this will be the final velocity squared, plus mg and the final height. So this is the total energy on the left-hand side. Total energy. This is kinetic and that's potential. Must equal the total energy on the right-hand side. Excuse me. And all energies have the units of a joule. So that'll be in joule, that'll be in joule, that'll be in joule, and that one, these two here will also be in joules. And lastly, we have power. P represents power, is equal to the work done. And that work, in order to put that work right here, is this equation up here. So we can put Fs here, because that is the right-hand side of work, divided by the time. And the time has to be in seconds. And work is a form of energy, so it has to be in joules. So if we look at this, and we have the units on the right-hand side of joules per second. And a joule per second has a special name known as a watt, named after James Watt. So power has a unit of watts, or joules per second. And if we look at our base unit sheets, there we go, going down. Here's the watt, and it has joules per second. Let's say here one more time, it says power. Here it is, power. Power has a unit of a watt, and a watt is represented by the capital W, and it is a joule per second. Going back to our equation, I have to make a little fold. Power, work, and work, as I said, is here, and it's F times S, and that F, that force, is all of these forces can be substituted into here, and then that work can be substituted into here, giving us power for a variety of different methods. And hence the reason we have here, work is divided by time. And the right-hand side of work is force times distance divided by time. And this force is the same as this force here, which represents all of these forces. And it's just a matter of substituting depending on which one we are using at the time. And power, as I said, all work is energy, unit of a Newton times seconds, and that is a watt. And that takes care of our equations for this sheet.